Okay, so the next oscillator, or the next oscillator we're going to talk about is the Colpitts oscillator. Now, when you look at the, so hopefully you went through some of the PowerPoint slides and you read on your own to get an idea what's going on. Now, I'm showing the simplified version with the capacitors to ground, right? Omitting the inductor for a second, right? Because this was the original configuration. Now in this configuration, the idea here is that once the oscillator is triggered, now remember all oscillators have to be triggered at some point. Once it's triggered, right, we know that this is your basic common emitter amplifier, right? We know that the output, whatever the output is at this point, right, this point will be 180 degrees out of phase. Now don't worry about RFC for a second. We'll talk about that. That means radio frequency choke, but it's an inductor. But we'll talk about that later in the lesson, so don't worry about him just yet. Now, so we have an input, and we have an output 180 degrees, and then we have this crazy network where there's a parallel combination, right, of capacitance and inductance with a tap to ground here, and then the feedback network that comes back around. Now, what I'm going to illustrate in this lesson is how it is that we get exactly 180, since we're 180 degrees phase shifted, and we know we need positive feedback. How do we get it 180 degrees back around? I'll use this simplified diagram here. So I'm omitting the inductor for a second. You can see that this guy would, right, based on his criteria for charging, we'll just say he's charging negatively and positively, while at the same time this guy would have a positive to negative charge. Okay, so you got these two capacitors. So that alone, the fact that one is charging negatively, because you can see, but so let's just pick this point. As the signal comes in, he charges negatively and then discharges, right? This guy, he sees the peak signal, so he's charging positively. Okay, now how the inductor plays, right? So we can see that if we redraw the circuit, you can clearly see that C1 is V out, C2 is V in, right? And that's just taking this concept of where the ground is. Now where the inductor comes into play is if we redraw this, essentially, right? So keeping in mind, all I'm doing is a straight path across from ground to ground, right? So from this ground here, I'm following this path all the way around through the inductor and back to ground. What you essentially have is this coil with two capacitors, right, on either end, right? One would be C1, the other one would be C2. Okay, so you have, and you can see just based on what our charging criteria is, if this guy's charging negatively, positively ground, this guy's charging positively, negatively ground, you can see that if you can imagine the inductor as a power supply, right, his charge would be something like this, and he would be always opposing the discharging of the capacitors. Okay, so what we have essentially is the inductor in parallel, right, with two discharging, or essentially in series, sorry, with two discharging capacitors. Okay, and that's how you can see the input and the output and how the feedback network works. Now, one thing to keep in mind is that the feedback network gain, right, is found by XC2 over XC1. Now remember, whatever that ratio is, we just got to make, whatever that ratio is, we just got to make sure it basically, again, I'm going to hammer this point home, but you got to make sure that whatever the amplifier gain, whatever AV is, right? Again, let's use the 100. So in this amplifier, if the input gets amplified 100 times, right? So if you have 1 volt peak, it goes to 100 volts peak on the output. We just have to make sure that our gain, or our feedback gets, our gain overall in our feedback network reduces everything back down to 1. okay? Now, because XC and XC2 are reciprocals of the capacitance, you can also state this formula as just C1 over C2, okay? If I wanted to solve this circuit further, I could solve for what is the resonant frequency of this circuit by simply, implying our resonant frequency, right? Sorry, it's supposed to be R, is equal to 1 over 2 pi square root LC. And in this circumstance, you'd have to find total capacitance first. And remember, these guys are technically in series, and this one's in parallel, so you'd have to do the product sum method of this one to find total capacitance, and then implement whatever the coil is to get your resonant frequency.